In the name of Almighty God, I'm Master Sankashi, and today I want to talk about interactions between hydrogen and palladium nanoparticles resolving adsorption and absorption contributions. It was written by Lillian and his colleagues despite the apparent simplicity of palladium hydride systems. Interactions between hydrogen and palladium are multifaceted. Electrochemical hydrogen stripping allows measuring the stoichiometric coefficients of hydrogen atoms inside palladium hydrogen X structures whose properties greatly depend on X. In this paper, the insertion of hydrogen into palladium nanoparticles has been studied in a three-electrode setup (RDE) and a proton pump cell. An original way of modeling the hydrogen desorption curve is proposed, helping in the separation of hydrogen absorption from other contributions. The loading voltage exhibits the highest impact on the hydrogen absorption into palladium, reaching hydrogen absorption per palladium up to 0.47, positive negative 0.02 in the RDE setup at minus 0.2 VRHE. Conservatively, the loading duration presents only little influence in the very first seconds. Finally, maximal hydrogen absorption per palladium ratios are measured around 30 up to 40 degrees of centigrade, likely due to an optimal balance between the hydrogen absorption rate and hydrogen diffusion rate into palladium. Now I want to go through the introduction. Palladium has been truly studied for its remarkable behavior in presence of hydrogen due to its ability to absorb large volumetric quantities of hydrogen under ambient conditions. Palladium has been investigated for many hydrogen-related applications, including hydrogen storage or enhanced spillover, hydrogen purification, and hydrogen sensors or catalysts purposes. Other applications that take advantage of changes in the electrical, magnetic, mechanical, and or optical properties of palladium hydride could also be considered in the future. Palladium catalyzes in a face-center cubic structure with four octahedral and 8 tetrahedral interstitial sites per unit cell. Before forming a metal hydride system, protons undergo an adsorption process according to the Volmer reaction equation 1. Hereafter, in acidic media, positive hydrogen plus palladium plus one electron has a bidirectional to palladium and hydrogen absorption, where palladium is the absorption site and palladium hydrogen absorption is a hydrogen atom absorbed on the palladium surface. Under standard conditions, two distinct phenomena are differentiated. The first one is the under potential at the position of hydrogen, taking place at potentials more positive than the thermodynamic reversible potential of the hydrogen evolution reaction. For example, 0 volt versus RHE. The second one is the over potential deposition of hydrogen taking place at potential below HER. The HUP palladium is characterized the characteristics of a very limited category of noble metals, including uh, platinum, RH, IR, and palladium. HOPD is described as the intermediate species to the hydrogen evolution reaction. It is generally accepted that the absorption of hydrogen in the palladium bulk presents an intermediary stage where hydrogen atoms are located in subsurface positions. Equation 2. Palladium hydrogen absorption and palladium substance has a bidirectional to palladium surface plus palladium hydrogen subsurface. Afterwards, hydrogen atoms are expected to diffuse in the palladium bulk by jumping from the octahedral site to another. Equation 3. Palladium hydrogen sub has a bidirectional to palladium absorption in parallel to the absorption process. Absorbed hydrogen can also react to form gases dehydrogen following two different paths. The Hierowski reaction in equation 4, for example, electrochemical desorption or electroreduction. We have equation 4, palladium hydrogen adsorption plus one hydrogen ionized positive plus one electron has a bidirectional to palladium and hydrogen 2. The Tefal reaction, equation 5, for example, non-electrochemical removal or recombination. 2 palladium hydrogen absorption has a bidirection to 2 palladium and plus 1 hydrogen. Some studies also propose a direct absorption of hydrogen from the electrolyte to a subsurface position. This has been experimentally evidenced by poisoning the surface of palladium thin films with crystal violet, which doesn't hinder the hydrogen absorption. Even tau hydrogen absorption is greatly reduced. The overall mechanism may involve both direct and indirect absorption of hydrogen in unknown proportions, even if the kinetic rate of the direct absorptions has been proposed to be faster than the indirect one. Figure 1 gathers the first reactions taking place on the palladium nanoparticles in contact with protons. It is well known that palladium hydride, palladium hydrogen X can be found in at least three different phases depending on the proportion of hydrogen present in its structure. For X is less than 0.05, palladium hydrogen constitutes a solid solution named alpha phase. Between approximately X is greater than 0.05 and X is less than 0.7, palladium hydrogen is constituted of a mix between the alpha and beta phases. Above X is equal to 0.7, the beta phase is suggested to be the only one remaining. An additional gamma phase is more rarely considered, which could start appearing for X greater than 0.7 mixed with the beta phase. The hydrogen loaded into the palladium lattice is often presented as the molar hydrogen per palladium ratio is a critical parameter to estimate as many properties of the palladium hydrogen system vary with X. Several ways to measure the hydrogen per palladium ratio have been presented throughout the years based on the different properties of palladium hydrogen X system, for example, increase in resistivity, mass, and lattice parameters. More recently, electrochemical methods have been widely used, mostly based on recording hydrogen desorptions at a constant potential. However, each technique has its pros and cons and limitations that are worth considering. The resistance ratio method has been used for many decades and takes advantage of a dependence of palladium hydrogen X electrical resistivity on hydrogen concentrations, which shows a maximum at X is equal to 0.7. However, above this concentration, the palladium hydrogen X resistivity decreases, thus implying the existence of the two possible compositions for the same resistivity ratio. In addition, the palladium hydrogen resistivity is greatly influenced by external physical parameters, for example, temperature variations. Nonetheless, this technique is a fairly simple way to estimate the hydrogen palladium ratio in situ. The gravimetric method utilizes the increase in mass between palladium hydrogen X and bare palladium electron, rarely encountered in the literature. This approach takes a significant amount of time to be carried out, as results should be repeated several times for higher accuracy. Some limitations arise from the use of this method. Only bulk electrodes can be weighted with the sufficient accuracy to determine the mass difference. Thus, implying long loading durations. Hydrogen atoms start to naturally recombine as soon as the loading potential is turned off, leading to the underestimating results. While outside of the electrolyte, the electrode can be affected by the ambient atmosphere, for example, undergo water absorptions in operando measurements of the palladium hydrogen lattice parameters using X-ray diffractions. XRD has been shown to be one of the most accurate techniques to measure the hydrogen palladium ratio when hydrogen atoms are inserted into the interstitial positions of the palladium lattice and expansion of the lattice parameters is observed. Yet, access to this method is made difficult by unconventional electrochemical cells that it demands and availability of high energy X-ray beams such as in the synchrotron facilities necessary to analyze the inside of the cell under operation with a fast time resolution. The colorimetric stripping method is widely used in the literature to quantify the quantity of hydrogen absorption onto the palladium surface and absorbed inside the bulk of the material. Commonly, this method is used in a three-electrode setup with the palladium catalyst deposited on the working electron. A potential negative enough to load the palladium with hydrogen is applied, typically around minus zero point 0.1 voltage RHE before switching the applied potential to a value positive enough to absorb the desorption of hydrogen, typically between zero point 0.4 VRHE and 0.65 VRHE. This in situ method is easy to set up, allows a wide variety of a small volume setups as well as a wide variety of materials, nanoparticles, thin films, and wires. And other demand calibration or complex instrumentation. Additionally, this technique is usually quite fast, for example, a few minutes is sensitive and allows many different sets of experimental conditions, for example, different temperatures, feeding gases, gas contaminants, the overall quantity of hydrogen atoms stored onto or into the palladium structure is calculated by integrating the current passed during the desorption step. However, significant contribution from the hydrogen oxidation reaction is also part of the desorption curves due to the presence of evolved hydrogen in the Davili surroundings or trapped into the microstructures, resulting in an overestimation of the hydrogen palladium ratio. Some research works have been focusing on limiting the contribution of HOR or hydrogen oxidation reaction while which, for example, the use of the electrochemical flow cell to displace hydrogen bubbles from the surface of the WE. It was also shown that the bubbling the electrolyte with an inert gas and or using a rotating this electrode is an efficient way to greatly decrease the accumulation of hydrogen on the WE and thus limiting its oxidation during the deposit desorption setup. In earlier studies, the group of Lysol and his colleagues has proposed a method to separate the contributions of hydrogen absorption and hydrogen absorption in palladium thin films between 20 and up to 80 nanometer. It was revealed that for increasing film thickness, if the hydrogen absorption is similar and only related to the electrode surface area, the absorption represents an increasing portion of the total charge during the desorption. However, no investigations was carried out in the case of the palladium nanoparticles, for which the direct estimation of the surface phenomena is hindered by the use of a support material which contributes to the double layer capacitance. The group of Sazarvinsky and his colleagues studied the adsorption and absorption of hydrogen on and in the palladium thin film ground gold and silver in presence of the monoxide carbon. After saturating the palladium sample with hydrogen and carbon monoxide can be injected, which results in a positive oxidation current. That's the others attributed to the oxidation of hydrogen as it is replaced by the carbon monoxide molecules. However, it stays unclear what proportion of the absorption hydrogen goes undetected by this method, as some atoms undergo a non-electrochemical removal. In this paper, we propose an original and easy way to decompose the desorption curves recorded during the colorimetric stripping analysis to extract the contribution from the hydrogen actually absorbed into the palladium lattice. Additionally, hydrogen absorption has been performed in both liquid electrolyte and proton pump setup, the latter allowing it to reach a much lower voltage up to the minus zero point 0.5 volt, and thus exploring the region rarely studied. An extensive investigation of the influence of the loading voltage, the loading duration, and the setup temperature on the absorption of hydrogen into palladium NPEs has been carried out, leading to a better comprehension of the overall mechanisms. Palladium NPEs have been preferred to palladium thin films due to their extensive use in numerous applications, especially in the field of the electrocatalysts, for example, carbon dioxide reduction, where their size and composition play a very significant role in the reaction mechanism. Now I want to talk about the results and discussions. Modeling of the desorption curves. The desorption curves recorded at constant potentials positive zero point 0.4 volt have been modeled following a simple procedures based on the diffusion of different hydrogen species to the surface of palladium particles and their subsequent desorption in the form of the proton and electrons through either the Volmer and or Hayrovsky reactions. The resulting current is thereafter compared with the experimental data. For the sake of simplicity, reactions occurring during the adsorption process are assumed to be of the first order. This assumption is based on the fundamental studies which show that the desorption of hydrogen atoms from the palladium 100 follows a quasi-first order kinetics. However, for a lower hydrogen coverage, the hydrogen desorption is a second order reaction, which might explain some small discrepancies between the model and experimental data at low current densities. In addition, it was established that the migration of hydrogen atoms on the palladium surface, for example, due to an electric field gradient, is a first-order reaction, which also supports the decision to use first-order kinetics for the diffusion of hydrogen atoms to the palladium surface. Additionally, as a potential difference applied acts as a driving force towards the desorption of hydrogen absorption, the following reactions are assumed to be non-reversible. The couplets of reactions are first considered. See, for example, figure 2, describing the two-step diffusion to the palladium surface of the first one is hydrogen atoms absorbed into the palladium lattice. The next one is hydrogen atoms absorbed on the surrounding carbon support hydrogen spillover, and the third one is the dehydrogen in the vicinity of palladium NPS evolved during the electrochemical loading step. As the surface of the palladium NPS is limited and firstly occupied by absorbed hydrogens, these two-step reactions have been used to express the existence of intermediary buffer positions from which hydrogen atoms can readily react to form absorbed hydrogens. In parallel, absorbed hydrogen atoms undergo desorptions according to the Volmer reactions. Equation 6 hydrogen adsorptions includes hydrogen ionized positive plus one electron. The three sets of equations are used to calculate the quantity of each species at a specific time. The decrease in the quantity of a species in the bulk positions noted each bulk, for example, applied for the hydrogen absorption and hydrogen bulk and hydrogen spillover, is calculated according to the equations 7 and 8. The general reaction rate constant must be replaced by the corresponding one from figure 2. Delta t corresponds to the time difference between the two successive points, which are respectively indicated with the subscripts. The quantity of intermediary species noted hydrogen integration, for example, applied for hydrogen surface and hydrogen 2 surface and hydrogen spillover surface, both increases and decreases due to the diffusion of bulk species and the formation of hydrogen absorption respectively. The overall change is calculated as follows. For example, equation 9 and 10, where Km should be replaced by the corresponding reaction rate constant from figure 2. The amount of hydrogen absorption is depending on the rate at which it is consumed to form hydrogen positive, as well as the rates at which the intermediary species participate in the replenishment of this absorbed layer. The change in quantity can be calculated according to equation 11 and 12. Finally, the current resulting from the whole process can be computed by assuming that each hydrogen absorption atom reacts to give one electron. Therefore, it is possible to convert the molar quantities of the desorbed hydrogen into an equivalent number of electrons, leading to the following equations 13, considering all the replenishment and depleted described in the model, where delta x T minus 1 is molar quantity difference of the species X between the two successive points at the T minus 1 and T. The resulting current can be calculated with the equation 14. To provide a good fit of the data, the availability of the palladium surface had to be considered in the case of the spillover contribution, as hydrogen atoms cannot diffuse from the carbon surface to any available positions on the palladium surface. It is proposed that only a fraction of the palladium surface is accessible to hydrogen spillover diffusion, describing that only a fraction of the palladium MP surface is directly in contact with its support. To represent this behavior, a coverage parameter has been introduced ranging from 0 to 0 to 1 when multiplied by the initial quantity of hydrogen absorption. For example, when the surface is saturated, it gives a maximum limit above which the surface is not considered available for the hydrogen spill diffusion. Coverage values were determined from the current derivative curves by centering the calculated peak associated with the spillover contributions with respect to the experimental data. An example is provided in as two typical coverage values were found between 0.3 and 0.5. In addition, it is considered that the quantity of hydrogen absorption at all times cannot surpass its initial value, which is assumed to correspond to the saturation of the palladium surface with hydrogen atoms. In case of oversaturation, the difference between the actual amount of hydrogen absorption and hydrogen absorption zero is given back to hydrogen subsurface and hydrogen spillover surface, and or a hydrogen surface, depending on the contributions participating at this specific moment. The initial parameters of the model, for example, initial quantities, hydrogen bulk and hydrogen intermediates, and reaction rate constant X3, are optimized using the solver functions of Excel by minimizing the absolute difference between experimental and calculated data. In practice, the initial quantities of intermediary species, for example, hydrogen subsurface, hydrogen spillover surface, were kept equal to zero, reducing the number of variables in the model. The simplification of reality is still pertinent, as few hydrogen atoms are in direct contact with the palladium surface in the very first instance. For all the other parameters, the values were first manually inserted in the model and then allowed to be modified during the optimization. Non-specific boundaries, in addition to the one described before, were necessary to perform the fitting. The sensitivity of the model was tested in a positive negative 10% range around the optimized parameter. The resulting errors are represented depth by a colored area around the calculation contributions. Electrochemical analysis of the proton pumps. Proton pump, often referred as electrochemical hydrogen compressors, are generally used to purify and pressurize hydrogen up to several hundred bars. So thank you so much for watching my tutorial video until the end. Today is the 5th day of July 2026, and in the morning, if there is any simulations for this literature, you can find and download it from the github.com/mahsa script or /kashi script or /safra script.